Okay. Everybody sits. Welcome everybody to our first Rook talk, and welcome Alexander, the Rook maintainer.
Thank you. Yeah, so my name is Alexander Trost. I'm a, Rook maintainer. I'm just decided I'm a DevOps engineer at Cloudability. And today I'm kind of going over using Rook, using Rook in Kubernetes to run Ceph in Kubernetes, and kind of going into like what are the advantages of doing that. And yeah, from a general side, kind of like what is Rook, a bit of the architecture of Rook, a bit into like the integration with Kubernetes. That in the end, most of the time you want to use the Ceph storage you're running with Rook inside of your Kubernetes cluster for your applications. Let's say, I don't know, like a MySQL database or something. And then, the advantage is kind of like, how can it help you doing that? And one part which probably falls flat due to technical issues with my laptop. I'll see if I can get some video or something up that we kind of get a demo of the creation of a cluster, and also how easy it is then in Kubernetes to consume the storage there, and you're adding and removing a new node to the cluster, to the Ceph cluster in the end. I have to see. Yeah, and in the end, just like a why Rook, a few more points there, and yeah. So, Rook is a cloud-native storage orchestrator. Cloud-native, everybody talks about it. It's this cool cloud thing, you know. It's specifically made for being run in Kubernetes. Which simply in the end implies that it's in a container. So it's basically a cloud-native container storage orchestrator. And through this orchestration, Rook can run, for example, Ceph, but also other storage softwares, which I will come back later on, for you in your Kubernetes cluster. The special point which Kubernetes allows through the extensibility of the Kubernetes API is that you have the possibility of create your own custom types, and also, in the end, controllers which react to these custom types in Kubernetes. More on that later. And in general, the goal here is that for the orchestration part, we try to have the deployment automated as best as possible, bootstrapping of the software, for example, in this case, Ceph cluster, the configuration, provisioning, scaling, upgrading, migration, disaster recovery, monitoring, and resource management. Those are all points which we try to cover. Not all of them, those points are covered yet, but it's open source. We are happy to see people help us reach the goal of full automation of your, for example, Ceph cluster in Kubernetes. As I already said a bit earlier, Rook is not only Ceph. Ceph is one of the many storage providers that Rook can run for you. For example, MinIO, which is the object storage, maybe you've heard about it. Then there's also, from the Nexenta guys, it was HFS. It's kind of in the direction of like Ceph, which provides block storage, file storage, and also object storage, but in a more like, I think they have a huge point in like GEO replication by default kind of in it. Definitely worth to check it out. And some other too, which I have later on the slide, which are currently on in Rook. It's, with FOSDEM, it's open source. It's especially what is good for us, it's hosted by the Cloud Native Computing Foundation. It's currently in the incubator state of the CNCF project level. Rook framework. as Rook is not only there for just running Ceph, but also for MinIO, EdgeFS, and so on, Rook tries to get a generalization of certain types which are common across those multiple storage backends. So for example, to say it with, for example, Ceph and EdgeFS, the selection of the devices on nodes is the same. There are no two types which are different. This is one type where we basically have a list with some more details, which we go in later too, of which devices to use. And only already with those common specifications, specs used between multiple storage providers, it's most of the time pretty easy to, well, not that I would recommend it too much that you, instead of like distro hopping, that you storage software hop all the time, but in the end something like that would be possible, because you could just copy and paste the device list from, well, Ceph, for example, into EdgeFS, or, well, back again. Yeah. With the framework part of Rook there, we not only try to have this common ground of specifications, we simply also try to have combined testing efforts that makes it easier for all those platforms which have their own operator in Rook to be, well, tested together, have policies and stuff, just share the code. That is not like every operator which, for example, would run something like Ceph, like EdgeFS, and other possible software backends, software storage backends, that they don't need to write that from scratch all the time. So that's one of the goals with the Rook framework, basically there. Yeah. The architecture of Rook, it's going a bit into Kubernetes right now here, as we're kind of a general look right now here. We have the Kubernetes API. We have our client utility, which we can use to talk with the Kubernetes API. And for, well, Kubernetes uses etc for the data store of the API objects. And if we basically start from here, we have our client utility with which we tell the Kubernetes API, we tell them about these new objects. So that in the end, we end up with objects like Ceph cluster, Ceph block pool, Ceph object server, Ceph file system, and, well, for the other operators, if you install them too, obviously those two. When we have created those objects, we can access them again, just run it like, for those knowing about kubectl, like kubectl get Ceph cluster, and we get the object as it is currently in the API, and in more common, more current releases of Kubernetes, I think with 12, 13 or so, you even get some more information about the object as it is if you simply run the kubectl get to, well, retrieve the object from the Kubernetes API, so that you have a quicker overview of has it been created successfully, how many monitors am I running, and just some general information. Moving on to the operators. As said, with the multiple storage backends, for example, we have the Ceph operator there then, with MinIO operator and so on, for each storage backend their own operator. And the operator basically takes care of creating the deployments, the daemon sets, and all that is needed to run the storage software. So for Ceph, that would be creating deployments for the monitors, creating deployments for the OSDs, and all other components like manager, OSD, MDS, RGV, and then also, for example, configure certain aspects in the manager, like enable the dashboard, and, for example, enable SSL on it, disable SSL on it, stuff like that. And it's making it simple by, this is possible, again, because we have one common object, the Ceph cluster object here. We have this one object with which the Rook operator knows how to handle it and has all the options we support in it, which you can just go ahead edit for not all options right now, but for a good amount of options you can go ahead like toggle the dashboard on the fly. If you have it on false when you created the cluster initially, you can just go edit it, put through in, apply it against the Kubernetes API, and the Rook operator will pick up this change and do its thing and enable the dashboard. Now, moving on to this part here, this is basically like we are on the node right now. Where did we have here? The daemons are obviously for, let's say, for example, Ceph. We have a monitor, an OSD, or well, one of the Ceph daemons, which is placed on a node. If well, a mon is placed, and do you want to use the disks on a node, also for storage, you would well obviously also have OSD daemons running on that. But all containerized, so there's no like well conflict with other stuff running on the system. It's well in containers, so. Well, there are certain differences between which container runtime you use from the isolation level, but they're isolated at least. So the container part there is also the point where the upgrading for Rook is also making it easier, because we just go ahead in the deployment, which for example would run an OSD there, would just go ahead to the Kubernetes API and say, hey, change the image from Ceph version 12 something to version 13 something. And for the other DMs, basically the same update aspect comes in place too, because Kubernetes does this management for us. Then there's also the Rook agent. The Rook agent is, in our current case, the so-called Rook Flex Volume provider, a plugin provider. This is, well, Flex Volume is kind of like the predecessor of CSI, kind of in Kubernetes, where CSI is the container storage interface, which, well, kind of, as the name implies, is like a common interface for storage, not only a thing for containers, but in general for storage. And Flex Volume is kind of like that too, but more on a limited scale, as I know, especially for Kubernetes there. And we have it running right now still with Flex Volume, but it's more or less to the point because of Kubernetes with having CSI support on beta or stable with version 1.13. And we're, well, currently supporting like the last 3 versions of Kubernetes, so we still have to have the Flex Volume. But to the Flex Volume here, if I have a pod which wants to use a volume on this node, the kubelet, the node component of Kubernetes, would call out to a socket on a node, a Flex Volume socket, and then the Rook agent would receive this request and then, well, go ahead, get the information of the volume and do the RBD mapping and then the RBD mounting. One quick note, the kubelet, I think, is in most cases doing the formatting of the volume. So, I think formatting is done by the kubelet, which,
I'm not sure if you're going to tell us more about this or not, but for instance, OSDs on Ceph need access to the block devices. Is this accomplished with Flex Volume, or will it be accomplished with the new CSI stuff?
I'm trying to understand the question, sir. So you mean the block device, if I map the volume?
No,
so
the
OSDs.
The OSDs
Yes.
themselves, they are backed by the disks.
Yes.
Right? Where they write the objects and all that stuff. So the containers will need to have those block devices exposed to the container, right?
Okay, so if I understand correctly, the question is that how are the OSDs able or getting the access to the block devices? Well, right now it is simply done by mounting the /dev of the host into the container. There are ways, I think, especially through what was it? Local persistent storage, storage from Kubernetes, which has been introduced, I think, like 1.9, 1.8, I think. 1.9? Yeah. Which could potentially be used for this exactly purpose. We are still kind of looking into how we can make it use it like this, but we're kind of like right now /dev is basically working for us out. So, but we also already at least looking into restricting the /dev access to just the device and or the partitions that are on this disk and for the Ceph OSD. But there's still a good amount of work to do to get there. But yeah.
Thank you.
So yeah. So if I create the Rook Ceph operator and then go ahead and create a Rook Ceph cluster object too, well, I have, as already said in the previous example here, we have the agent pod, which is running in all nodes. And the operator then, as said, takes care of creating the Ceph component parts, like the OSDs, the monitors, manager, MDS, RGB is also there. And, well, in the end, you have a Ceph cluster with that. Yeah. So, to summarize this part, we have this custom object with kind Ceph cluster, which the Rook operator, the Rook Ceph operator has defined. You create it, and what you currently with that would get is we're a Ceph cluster running Ceph version 13.2.4 something something, and ignoring the data, data host path in Rook is right now where most config is stored and monitor data, but we're working on trying to, make it really just for configuration. Still mon data, but not OSDs. Because right now the behavior would be that if you don't specify like disks and anything else, you would get an OSD using a directory of, basically a file store directory OSD, which, if you have this from performance-wise is way better. The disk one is way better. Yeah, but coming back here, we have like the dashboard part here where we say, yeah, we want the dashboard, so we have enabled true. We can control a bit about the monitors, like how many do we want. If we want multiple monitors on one node, this is if you have, only 3 nodes, you may or may not want this to happen. Or if you have multiple nodes, you normally want to disable this more than 3 nodes, for example, because then you already always have room to move a monitor from a node which failed to another node and, create a new monitor there, basically. This part with the storage here is here, for example, use all nodes, use all devices, is kind of like controlling. There's more to control, but those 2 options are kind of allowing you to select where storage will be used and what storage will be used. With the use all nodes, it's kind of, use all nodes that the Rook operator can place OSDs on it, which are, to put it like that, valid in Kubernetes aspect. Use all nodes would imply that all empty devices will be used for an OSD. And if we, I didn't upload the latest one. If we go, if we skip a few slides ahead, we come back again to this storage configuration part where we have, again, those use all nodes and use all devices. Instead of, for example, having use all nodes true, that all nodes which are applicable will be used, we could also specify a list of nodes, which I'll have information on the next slide. We can also have a simple device filter where we go, yeah, use all disks with SD and, wildcard, basically. And then Rook will take all disks with this matching regex, besides disks that are not empty. There's also possibility to specify certain configuration parameters, not only in a cluster-wide level, but also on a node and even OSD part level, where in this case, for example, we have like an option which normally is only used for NVMe or, faster than SSDs devices, is the how many OSDs should be created per device. And if we go just one further, we are at the nodes list here, and there you can see that, for example, you have this node. You say, use a directory, have those resource limits in place from Kubernetes side, that container, the OSD container for this for this node, as it's on the node level here, will have those resource limits in place. Then, for example, here with a device, you have the node name, and in this case specifically say, hey, use SDB. But you can also, again, if it would be, for example, an NVMe, as it's the second device here, you could then specify like config and then OSDs per device like 3, or well, insert a math for NVMe devices, how many OSDs here, basically. There we even have it, OSDs per device, where you can just have it per device and on node level, on cluster-wide level. So that's not all. Just have to find where I left off. Yeah. Yeah. To shortly go into the further Kubernetes native integration part, besides the so-called custom resource definition, those custom types, objects we can create, we already have in Kubernetes storage classes, which allow us, the admin most of the time, to specify which provisioner and certain parameters for this provisioner to be called. The provisioner will be called if you create a volume now, a persistent volume claim. If it matches this storage class, if it has this storage class in it, Kubernetes will take care of talking with the provisioner and saying, hey, somebody requested 20 gigs of storage, for example. If you go one further here, this example with 20 gigabytes of storage. And here we specify the storage class name, so we especially use the one we just saw. If we create this, this will result in 20 gigabytes of storage. That's kind of where Kubernetes takes over in point of like storage management, as Kubernetes has all the persistent volume claims, which are, I hope for everyone using them, always reflect the claims an application has made. Like, hey, I need 500 gigs of storage. So it's always, this application is using 500 gigs of storage. And in the background, as kind of like a not on Perl application level, you have the persistent volumes, which are, again, also having the information like which storage class has been used to create this volume, how much storage is this actually, what access mode is used. Like Kubernetes has 3 access modes, where the first is read, write once, which is, well, only one can read and write to it. The second is read, write many, where, well, many can read and write at any time at the same time. And there is read only many, which, well, many can read only at the same time. This we had. Yeah. So what can Rook kind of do to make it, well, if you have a Ceph cluster, especially because, well, you need to run a Ceph cluster. Make it better for you to, well, run a Ceph cluster in Kubernetes. Well, especially, as I said, if you have one. If you don't have one and you're like, let's go, it might be a bit problematic because you need to know a bit of stuff of Kubernetes. It's, well, the simple fact that if you start one hire with a platform and then put it on, you should have knowledge about the platform. Part what Rook does is, as we heard, health checking for monitor. So if you have, let's say, 5 nodes, and you currently, just for simple example reasons, have your monitors, one on the first node, a second on the second, and third on the third, and the third node would fail, it would move this monitor, fail it in the Ceph cluster, and move it over to the, let's say, node 4 or 5, which are available for that. The simple management, simply through the Kubernetes API, in a second, through the Kubernetes API, in point that you have those YAML manifests, kind of, so, yeah, say and put it like this, with infrastructure as a code, kind of. It's, yeah, more and more, well, not only infrastructure as a code, but kind of application deployment as a code, depending on how far you see it. You have those YAML files which define how your Ceph cluster should look, how which pools should be created. You just have a YAML file which says here a pool object with this and this name, how many replication, should it use erasure coded, should it, which failure domain, which as a YAML object is, well, you just kubectl create it to the Kubernetes API and you have it. You have your pool created in a few seconds And it makes it easier on that side to, well, manage those things too. File system, for example, same here too. It's not like where you, oh, I want you to use file system. Let me buy 5 servers and install Ceph and, well, set up the MDS. With that, with Rook, well, you would need to put Kubernetes on it. And then just create a file system object which has the size numbers and everything, like for the pools, again, for this file system, but also numbers like how many active monitor MDS do you want, should there be a standby MDS2, and just gives you a bit of, well, playground, not to say like it, but a good amount of room to have certain options and have that automatically happen. Same for RGB. You have an object, you can control it through that, have certain options to control the behavior of the pools or how they should look. Yeah. And the third point I would like to bring up here is that, as we saw with the storage selection, again there you have a Ceph cluster object, you have either a list of nodes or more generalized a device filter or something where you say use those disks in for the cluster or even directories right now. Which, just as a side note for the storage selection, we have Travis Nielsen, which is also working on the Rook project, looking into enabling LVM kind of, well, with the Ceph volume, Ceph volume part, to be created, well, through Ceph code, Ceph code, and not as it was done since the release of 0.9. Now it's done not for all cases like that anymore, through Rook's own, well, OSD preparation, partitioning, formatting, and so on process. Well, we already went through that. Well, the YRook part is kind of covered by what you would get as benefits if you have a Kubernetes cluster for something like that. But so kind of in general, it simplifies certain tasks for the storage backend. There's, as said, still some work, like for example, replacing a node right now is still a bit of a manual process, but we're getting there. It's more or less that kind of a bit of a clash, like should we listen on the nodes that are in the cluster and then react if one goes missing, for example, or is already just not ready, or just some points where, for whatever reason, maybe an etcd issue or something, there's an empty node, so we go like, nothing to run, so just scrap it all, kind of. So, but well, as said, we're happy to just, well, see people maybe just chime in on the discussions on those topics. Yeah. Self-managing part is kind of that, well, we don't have liveness probes and readiness probes for all Ceph components, but I think we have it at least for the manager right now. And for the monitor, we do kind of external health checking from the operator side to see is this monitor still in form, or do we need to fail it over to a new node? Yeah. And the part with the dynamic provisioning there, that I create a claim, and a few seconds later, my block volume in Ceph has been created and linked with Kubernetes through the persistent volume object is, well, is a breeze to if you want to run with applications where you don't need to, like, well, fill in a ticket and say, hey, I need 20 gigs of storage. Can you please provide it to me? And someone starts running through the data center and tries to find a disk or something for you. But it's simply dynamic there, which is pretty good for, well, especially for developers. We're also interested with kind of like with the guys from Crossplane.io, Jared Watts and Bassam Tabara, if I got his name correctly. We're looking into also trying to get more abstraction in, like, for example, a developer would, I need a bucket, so he just creates a bucket object. And for example, we also have support for CockroachDB, so we would obviously, as a database, also want to look into having a database object which the developer would just create, and then in some way, which is kind of still up for discussion, should it be a service broker, should we do some magic, like in Kubernetes, well, mounting a directory into then the pod which contains the credentials, for example, then to this database or so. So again, there, if you want to kind of chime in there, we're happy to have discussion on that. The last point here in this list is, well, it's depending on how you see it. One problem I think which is still existing for AWS with their what was it, EBS block storage from Amazon. I think, what was it, the failover time was like when a node failed, it would take, I think, like 5 minutes or so to fail over to another node. And well, I hope you're only running cloud native applications, so it shouldn't be a problem as you have more than one replica. But it's still kind of a not too good number as you, even though it's cloud native and it should be okay with failure of a pod or even multiple pods in your cluster, multiple applications. It's still kind of a bummer to have like wait 5 minutes in the case of a failure of a pod. So that's kind of where I'm kind of saying it's less vendor login. Because well, you would run a Ceph cluster, which, yeah, on the one hand could also create more maintenance instead of, for example, taking care of just the EBS volumes of Amazon. But the failover is, in this case, for example, faster, or you just don't have to use their storage. Yeah. Yeah. As kind of said in the beginning, it's not only Ceph. There's not only a Rook Ceph operator. There's also a Rook MinIO operator, which well is object storage. So we have a MinIO object storage object. We have also CockroachDB, which well right now we only have a CockroachDB object, but again we are open for people commenting and discussing with us how we can go the best path, if it's more a service broker approach or another approach. EdgeFS has been implemented by the Nexenter guys. Just there again, also a big shout out to them, as it's a huge work. It's not like it's not like a MinIO where you have like 2 or 3 replicas of on a stateful set only, but there's again kind of like Ceph more complexity simply behind it, and it's amazing to see them have implemented it in Rook. Also, they're using certain parts of their Rook framework. And NFS server has MinIO and CockroachDB and, well, EdgeFS 2 implemented thanks to the community. So, yeah, well, I don't have the demo right now. Let me get to this page first. If you want to get involved, we are on GitHub. I think some people are still on GitHub, right? Not like with GitLab. We have a page which we are currently reworking. So if you're right now like, where do you find this and this? We're working on it. We know of the problem. And well, we have a Slack channel, it's a whole Slack for our own. Yeah, if you want to join. We also have a conferences channel. And well, if you have questions, a channel and so on. Well, Twitter, we still have a mailing list, I think. And there's community meetings every second week. Yeah. I would just jump to the questions right now.
Okay, so 2 questions. On one of your slides, you had there that you would allow multiple monitors per node. Is that correct, or am I misremembering?
So the question was that there's an option to run multiple monitors on the same node, right?
Yes.
Right. Yes?
I'm assuming that's for development purposes only?
There are certain people which probably run Rook with just 1 node and monitor count 3. So
Development purposes only?
Yes, officially and by development purpose only, yes.
Okay. The second question is about the monitor's failover.
Mm-hmm.
You're saying that if a monitor dies, it will be failed over to somewhere else. I'm fully aware that the monitors themselves are able to sync from an existing, at least as long as we still have one available monitor, it will be able to sync. But now I'm curious, what's the storage backend for those monitors?
Just your plain disk. So
Is that disk mounted to the container? Is Kubernetes itself or Rook managing to copy that data to some extent, or is it relying on the monitors' synchronization mechanisms?
Let me repeat the question. So the question is, for the mon failover, kind of how does the data get to the other node, or does the data even get copied from the node which failed to the other node, which is then the new monitor? No, it doesn't get copied. It's a brand new monitor, which, just a new directory, which, what was it, like just a mon host, send here, talk to them, and as you said, then the synchronization basically kicks in for monitors, and the new monitor should be, up to speed in a few seconds, I hope, at long.
You will still always need at least one monitor
Yeah.
lives, otherwise
Yes.
everyone's screwed. Okay.
Yep.
Just making sure.
Like a follow-up question for this.
Yeah.
What will happen with the pods that need storage? Will they wait for the new monitor to be up, or they will be redistributed to other nodes that already have the storage?
So the question is that if a monitor fails, what will kind of happen to the pods then that use storage? So from Ceph side, the monitor list is always kind of, to be like fluid. So if one monitor fails, it's still in the list of the configs most of the time. So if you bring up a new monitor and it's back in the, with talking with the other monitors, this new mon map is basically where the new monitors in it will be kind of distributed to the OSDs or the applications again. At least as far as I'm concerned. So.
Okay, so
Yeah.
you're literally creating a new monitor and not just reusing the same ID and IP.
Yes, we're creating a whole new.
You're basically destroying
Discussion for later, maybe. Other questions? Good question.
Yeah.
I have one. So you showed us how to deploy storage, but with software-defined storage, the network layer, like fine cluster to cluster, is also kind of important. How does that get defined?
Good question. So the question is, how does the network layer, how does the network kind of, what would be the network layer if you, for example, then put Ceph on it and you have like 5,000 other applications running in a cluster, right? Kind of.
Yeah, like how do you define fine public cluster networks?
Okay. So to kind of extend on what I just said for the question, it's going into the direction of separating the Ceph traffic, the replication traffic, and the client traffic. Right now, you would go and use host network mode, which, currently Kubernetes state is that you only have one interface per pod. If you use host network, you get a nodes network sect, which has other advantages and or disadvantages, to say it like this. But at least to go a bit further into the CNI part there for Kubernetes, there are multiple, I think 2 or 3 projects right now, which allow you to define multiple CNI plugins in your in a config somewhere, and then have multiple interfaces in your pods, which I think Intel, at least, I heard it from Intel at like Container Days, where they showed it off for like VoIP stuff and so on, and for them it seemed to work pretty good. But right now, host network would be the way to go. So, but yeah.
That's all we have time for.
Yeah.
Okay, let's give it up.